gate.
common drain.
Yes. Signal coming from the gate, taken out from the source. So it's known as a source follower as well. Common drain, yes, but it's also a source follower. And what it means is that the gain is non-inverting. That means it's in phase. The input and output will be in phase. So the gain is a positive gain. And the amount of the gain is always lesser than 1. Always lesser than 1. So these are some of the characteristics that you should be looking at. Why? Because when you calculate something, if the gain is more than 1, you know you're wrong. Okay, so there are certain characteristics of the amplifier that you must know, and this is one of them. Okay, so the gain is lesser than 1. Signal between the input and output is in phase, and and the output impedance is low. Okay, so here we are again asked to deal with the DC operating point, and therefore let's look at it. So here we are given this. We are given this circuit. So we're going to do a DC analysis. Therefore, we remove all capacitor because we are saying it's DC. So all the capacitor is of no value right now. And therefore, this is what you have. You only have this 2 resistor, this transistor, this resistor, and that's it. Okay. This goes to ground, this goes to VDD, and from here you can get the equivalent, which is your Thevenin's equivalent. Okay, this is what you're going to get, and this V equivalent is equal to VDD potentially divided across these 2 resistors, which happens to be R2 and R1. So therefore this is R1 over R1 plus R2. That is your V equivalent. Okay? Your R equivalent is basically this 2 resistors that is in parallel, because ultimately this will be AC ground. Okay? Your VDD will be AC ground. Your ground will be ground. Therefore, the 2 resistor is actually in parallel. Okay, so therefore, you would know your V equivalent, your R equivalent, and therefore you can take this loop to find out the current that you will be having at your source. Because your source current is the same as your drain current, and there's no gate current. Okay? And therefore, you can then write the equation that V equivalent, okay, is equal to IG R equivalent, which happens to be 0, okay, plus VGS plus ID RS. Okay, and that gives you one equation. And when we do this, we are assuming that the transistor is in the saturation region. Okay, and given that ID is equal to K over 2 into VGS minus VTN square. All right. We can then sub this into this equation and everything will be in VGS, or we sub VGS for ID and everything will be in equivalent to ID. So there will be a quadratic equation in VGS or quadratic equation in ID. In both cases, there will be two roots and you have to determine which of the roots is permissible and which is not. Okay? So let's take a look at it. Anyway, so we will end up, so this becomes V equivalent is equal to VGS plus IDRS, okay? And if we sub this into this, we will get an equation that is VGS is equal to 8.53 minus 3000 ID. Okay? I mean, we evaluate this. And you will end up with substituting the equation. You will get AN over 2 VGS minus VTN squared, which is equal to 0.001 over 2 into VGS minus 1 squared, where this is your Kn and this is your VT. Okay? And when you substitute this into this, you will end up with an equation which is ID is equal to 0.0005, okay, into 7.53 minus 3000 ID squared. And when you break this up, okay, to make your quadratic equation, you will get 4500 ID squared, okay, minus 23.59 ID, okay, plus 0.0285835, okay, equal to 0. So by using by using the equation ID is equal to minus b plus and minus root of b square minus plus 4ac, okay, over 2a, you will end up having a value that is 1.87 milli or 3.38 milli. Okay, one of these two values. So you need to substitute the two value into the equation on top, okay, and find out if VGS is a positive number or a negative number. Okay. So if we now sub in, if I say ID is equal to 1.87 milli, and you plug it in, you get VGS is equal to 8.53 multiplied by 3000 times ID, which is 1.87 milli, and that works out to be equal to 2.92 volt. Okay. And then if we use ID that is 3.38 milli, okay, then VGS is equal to 8.53 minus 3000 times 3.38 milli, and that works out to be minus 1.61 volt. So obviously this won't do, okay, because VGS must be greater than VT, which is 1 volt. So of course minus 1.61 will not satisfy that condition. Alright, so 2.92 is obviously higher than VT of 1 volt, so this will do. Okay, so based on this, we now take this VGS and find out VDS. So what is VDS? VDS is looking into this transistor with RS. Okay, so this is VDD, and VDS is equal to VDD minus IDRS. You take the entire VDD minus the voltage drop across RS, you will get the voltage across VDS. Alright? So this gives you a voltage that is 15 volt minus 1.87 milli times 3K. Okay? And that works out to be 9.39 volt. Therefore, if we look at it, VDS for a transistor to be in saturation, VDS must be greater than VGS minus VTN. Okay, VDS here is 9.39 and VGS is 2.92, and this is 1 volt. So this is correct, and therefore transistor is in saturation, and therefore the Q point is found to be a current of 1.87 milli at a voltage that is 9.39 volt. Okay, so that's your Q point. Okay? Now we will proceed with tutorial 8. Any question? We are in week 10. Ooh, getting closer. Okay, any question before we move on? So this is just doing the DC analysis. So why do we need to do DC analysis? So that we get Q point. Why do we need to do Q point? Okay, so this would be the characteristic of the transistor bias with VGS. Okay, and the Q point would be to find out this point. So the purpose of the Q point is because when we are operating along this line, okay, the transistor that propagate the signal through the transistor will be linear within this range, okay, because this line would be linear, okay, and therefore we can transverse the signal ID, okay, through this curve to generate VGS, or we can modulate VGS modulate VGS, so VGS will move within a certain boundary, and within this boundary, the signal between VGS and the current will be linearly related, okay? And this is based on the formulation that the small VGS must be smaller than 0.2 into capital VGS minus VTN. Remember we proved this formula? So this is the situation. In order for the signal to be linearly transmitted through the transistor, the small VGS cannot be more than this value or equal. Okay? And that's why we need to find out the Q point, because having the Q point, we will then know how much is this deviation, or rather this deviation here, which is your small VGS, okay, will be resolving between these two limits, so that the current that is generated through the movement of VGS, small VGS, will translate into a current that is linearly related to VGS. So that's the issue that we are dealing with. So for the next part, in tutorial 8, we will look into the AC analysis. So this is tutorial 8. So you see that the same question now appear again, but this time the DC analysis has already been done in tutorial 7, question 2. So now tutorial 8, question 1 is the same question, but we are going to deal with the AC instead of the DC. So the DC has already been done. So we make use of the DC, which is given here. ID is 1.87 with a VDS of 3.39, which is your Q point given to you. Alright, so this time we make use of this. Okay, so we are given that the resistor, this is still the same 3K. Okay, the two resistor is how much is it? 1.2 mech and 910 K, and this is 15 volt. Okay, and RL is 250 ohms. Okay, RI is 100 ohms. Okay, We are also given that Kn is 100 or rather 1 milli ampere per volt square, okay, and Vtn is 1 volt, and lambda is given to be 0.02 per volt, okay, and we are given the Q point to be 1.87 milli with a VDS that is 9.39 volt. Okay, so based on this, we can find out the GM. Okay, and the GM is given to be 2ID over VGS minus VTN, or is equal to root of 2I over K, sorry, 2I K, yeah, 2I K, right? And or it is also equal to, there's three former. You can substitute this equation in, and you will end up with K VGS VTN. Is it? 2 goes in, yeah. Okay, so these are the three forms of GM. Alright, and therefore if you look at this, what do you know? You know K, you know N, you know the current, and therefore you can make use of this one, for instance, and therefore you can find out the value, and that value would be, if you use this one, you will get root of 2 times 0.001, okay, times 1.87, okay, and that works out to be equal to 1.93 millisiemens, okay. We can find out R naught. R naught is equal to VDS plus 1 over lambda over ID, alright, and this is approximately equal to 1 over lambda ID if VDS is large compared to 1 over lambda, or compared to 1 over lambda where lambda is small, so 1 over lambda will be much bigger than VDS, and you will end up with this. And therefore, if you work this out, this would be roughly 1 over 0.02 times 1.87 milli, and that works out to be 26.7 K. Okay, and that's it. We can now draw the AC equivalent. So in doing the AC equivalent, VCC will go to ground, okay, and all capacitor will be shorted, and you will end up with this. And these two resistors will be in parallel, because they are both connected to ground, so R1 in parallel R2. And then it goes in to the gate, so it will end here, this is your gate, alright. On the other side, you have your source, which is at this end here. And the source will be connected to a current source. And this current source is going to point up, it's going to be VGS, GM VGS. The voltage that control the current source is your small VGS, okay, which is the voltage between the gate and source. And at the source is connected to your RS, which is 3K, and to your load resistance, which is your RL. So this is your 250, and this here is your 3K, okay, and this here is your 910 in parallel with 1.2 mech, okay, and this is 100 ohm, okay, and your GM is found to be 1.93 millisiemens, and therefore this is your AC equivalent. Okay, so if you go and find out what is the input impedance seen here, R in, okay,
VGS. Should be VGS. I think it's VGS.
therefore R in is equal to R1 in parallel with R2, which is 910 K in parallel with 1.2 meg, which is going to be equal to 517.54 K. Okay. Then you need to find out the terminal voltage gain. So what do you mean by terminal voltage gain? Is the gain between the two terminal between the gate and the source. That's the two terminal we are looking at. So the terminal voltage gain, AVT, is the voltage between the gate and the source. Okay? You need to find out AVT, terminal voltage gain. This is between the voltage at the output, which is Vs, over the voltage at the input, which is Vg. I mean, not the input, but the input to the transistor, Vg. And therefore, this is Vs, the voltage at this node. Okay? Is due to this current flowing through to these two resistors, and therefore is GM VGS multiplied by RS in parallel with RL. Okay. So that is your voltage at the output. Sorry, there is also another resistor here. My apologies. R0. Okay. So that is the voltage at Vs. Voltage at Vg, which is the voltage at this node, okay, is equal to the VGS itself okay, plus the current that is flowing through the three resistor. Okay. So now the voltage VGS is the voltage at VG S, which is this voltage, plus the voltage all the way from this node to ground. Okay, and therefore it is this voltage across the AC voltage across this is small VGS. Okay, so this small VGS plus the voltage from the source to ground. So that will be the voltage at the from the gate all the way to ground. So this is the voltage from the gate all the way to ground. It include VGS plus the voltage at the source, which is the current multiplied by the impedance across it. Alright. So over here the current terms is VGS, and therefore you have GM, okay, RS in parallel RL in parallel R0 over 1 plus GM RS in parallel RL in parallel R0. Okay, and if you work this out, this will be 1.93 okay, milli in parallel with 26.7 K, in parallel with 3K, in parallel with 250 ohm. Okay, and you have 1 plus 1.93 milli, okay, 2.26.7 K, 3K, 250 ohm. Okay, and this gives you a value that is 0.31. volt per mole.
I put
Okay?
because I drive a hybrid, but I'm not.
So to find out AV, the total voltage gain from input to output, which is from this node, which is V in, this is V in, okay, potentially divided to this node to get you your VG, and then from VG to the output you multiply by AVT. So you have a attenuation first from V in to VG, alright, and then from VG to V out, okay, or VS. So this here is from your VG, your V in to VG, okay, then from VG to VS, which happens to be V out. Same thing. Huh? So because of this, VG cancel, and this will be V out over V in. Okay? So in other words, this here is equal to potential divided value, okay, which is this divided by the total sum. Huh? So this gives you R1 in pair of R2 over Ri plus R1 in pair of R2. So this is your attenuator. It attenuates your input, alright? From the input to VG you have this, alright? Multiply by AVT. That will give you your overall voltage gain. Okay? So therefore this gives you just now we found the value is 517.54K divided by 100 ohm plus 157.54K multiplied by 0.31. Okay? And that works out to be 0.31 because this is just 100 ohm, okay, negligible. So you end up roughly the same, okay, roughly the same. So basically this here is R in over Ri plus R in. Okay. Then we are asked to find out the output impedance. So if you, in order to find out the output impedance, you kill the input source. So in killing the input source, you will end up having Ri, which is 100 ohm, 100 ohm, going to ground. And you have your R in, which is 517.54K going to your gate, alright, and at the source you have this current source here, you have your R0, you have your RS, you have your RL, and we want to find out R out. Okay, so R out, when you're dealing with R out, you don't include RL. Okay, and therefore, what we need to do is we apply a fictitious voltage across these two terminals, that is Vx, and measure the current that's going in, Ix. We take Vx divided by Ix, we will get the output impedance. Alright? So in so doing, we know that this current is GM-VGS. Okay? So this current is going in, this current is also going in, so the two current is flowing into this two resistor. So I can say that GM-VGS, okay, plus Ix is equal to the voltage drop. I mean this two current is flowing into this two resistor, which happens to be Vx divided by the total resistance here, because the voltage here is Vx. And therefore you can now write the equation. We also know that the voltage Vx is the same as the voltage between source and the gate. But the gate at this point is 0 because the input is shunt to ground. So therefore Vx is actually minus VGS now, given that the input is shunt to 0. Okay, we kill the input source, therefore this becomes the case, and therefore you can write the equation. Okay, instead of Vx you can put VGS, and therefore you can write that Ix is equal to Vx divided by R0 in parallel with Rs, okay, plus Gm Vx, okay, therefore this is equal to 1 over R0 in parallel with Rs plus Gm, okay, Vx. So if you now bring Vx over Ix, then this will give you a value that is R0 in parallel with Rs, okay, in parallel with 1 over Gm, okay, and that works out to be 26.7 K in parallel with 3 K in parallel with 1 over 1.93 milli, and that works out to be 434.6 ohm. So realize that the output impedance is low, okay? It's only in ohm, not in kilo or mega, all right? So that is your output impedance, R out, which is looking into this, okay? Next, we want to find out for signal operation, what is the signal voltage that you need, or rather, what is the voltage at the input that we need in order to satisfy the in order to make sure that VGS is smaller than, small VGS is smaller than 0.2 into capital VGS minus VT. Yeah? So in order to satisfy this, we such that the transistor is operating in the linear range, your small VGS must be smaller or equal to 0.2 into capital VGS minus VTN. Okay, so this is to ensure that the transistor is operating in the linear range, or linear operating region. We already found out that VGS from the tutorial 7, question 2, we already found out VGS is equal to 2.92 volt, okay? And therefore, your small VGS is actually equal to VG minus Vs, all right? We also know that we already found the relationship between Vs and Vg, and that is equal to AVT times Vg. Okay, in other words, this is Vg into 1 minus AVT. Okay, and therefore we can now write this is 1 minus AVT, and Vg is V in potentially divided through R in and Ri plus R in. Okay, and this would be Vg. Okay, and therefore we can substitute in that this is 1 minus 0.31, okay, into this is what, 517.54k divided by 100 plus 54k, which we say that is almost no different, and therefore this becomes 0.69 VI, okay, times 517.54k over 100 ohm plus 517.54k VI, okay, and this value must be smaller or equal to 0.2 into capital VGS minus VTN. And therefore you can now write this as 0.2 into 2.92 minus 1. Okay? And if you work this out, if you work this whole expression out, you find that 0.69 VI, which is this term, okay, will be smaller than 0.384. Okay, so VI must be smaller than 556.52 millivolts. So in other words, your V in or VI must be smaller than this value in order that the voltage at the gate to source is smaller than 0.2 into capital VGS minus VTN, to ensure that the transistor is operating in the linear range, no distortion. Okay, is that clear? Any question? Okay, I'll leave it here for a while. Any question?
This one there is a biscuit. Really big. Just use in the fridge. Yeah, it's very big.
No wonder. No one complain. We have no money to pay electric bill. Any question? Okay. So this question here, what configuration is this? What sort of transistor is this? It's a PMOS. What configuration? Yeah, it's a common gate. Signal is coming in from the source, taken out from the drain. Okay, so it's a common gate configuration. Okay, in this particular question, we are not given the Q point, so we have to do the DC analysis. Okay, we have to do the DC analysis. So first of all, let's look at this. This is okay, we are given this. So if I were to draw this, okay, I can put it in this manner. RS, okay, going into the source, coming out from the drain into minus VSS, and this is VDD,
Even.
and this is the gate
You.
going to ground.
Your even.
Signal is coming in from your input through RI, coming in from VI, taken out from the output into RL,
You start already.
and this is RD, and this is
How
RS,
many questions?
and there you are. And let's put in some numbers here. RI is 250,
Last time poly, start question 2. How many questions?
RL is RS is 68K. Okay, RL is 200K. RD is 43K. Okay, plus minus 15 volts. Okay, we are given that KP is 200 microvolt per microampere per volt square. Okay, VTP is 1 volt, and
Shouldn't you watch examination?
lambda is not given. Okay, lambda is not given. So when lambda is not given, we assume that it is if lambda is not given, what would we assume? What do we assume lambda to be? 1. 1 lambda is the channeling modulation term. So when you convert it to voltage, it's 1 over 1. If you put lambda as 1. Is it good? No! So I would rather have lambda equal to 0. Okay? So we assume lambda is equal to kosong, 0. So therefore 1 over lambda becomes infinite. Okay? So based on this, now we can first find out the DC. So the DC now becomes this. RS going to ground, RD, and this is minus 15 plus 15. Okay, so if I take this loop, okay, I would have 15 volt is equal to IDRS plus VSG is equal to 0. Okay, and if we assume that the transistor is in saturation, then ID is equal to K over 2, okay, into VSG minus VTP squared. Alright, so based on this, we can substitute in, and this will be equal to 2 times 10 to the minus 4 over 2 into VGS or VSG minus 1 squared. Okay, and we also have this equation here where we can find out ID is equal to VDD minus VSG over RS. Okay, we can then equate the two ID, and we end up with this equation. So this here is equal to 15, okay, minus VSG divided by RS, which is 68K. Okay, and therefore we can write the equation that this here is 10 to the minus 4 into VSG minus 1 square, okay, is equal to 15 plus 15 minus VSG into 68K. And you will end up with the 6.8 VSG squared, okay, minus 12.6 VSG, okay, minus 8.2 is equal to 0. And therefore, by making use of your, to find out the roots, you find that VSG is equal to 2.363 volt or minus 0.510. Okay? So based on this two, alright, you find that obviously this is impermissible. So only this, right? And therefore we can now take this equation and find out what is the ID. So ID is equal to K over 2 into VSG minus 1 squared, and that works out to have ID is equal to ID is equal to
how's your station up?
186
fast.
No, like going need to write.
microampere.
No,
Okay.
One day of
And
one day.
once we have this,
But
we can then take this equation and find out VDS. VDS or VSD is equal to VDD minus VSS, okay, minus ID across the two resistors. Okay, and that works out to be 15 plus 15, which is 30.
Sorry, what is it?
186 times 43K plus 86K. If you work this out, you find that the voltage is 9.35 volt.
No difference.
Okay. So we want to find out whether VSD is indeed greater than VSG minus 1
1 out of 5.
VT. Sorry. And this is equal
But the overall
to
result.
this side is 9.395 and this side is the value is 2.363 minus 1, which is 1.363. So yes, transistor is in
See
saturation.
how the report.
Okay. Transistor is in saturation. And therefore, we have the Q point given.
But you anyhow, right?
So the Q point
That's a key.
is
That's a key.
a current that is
No, not okay.
186
I thought just follow. Just follow.
microampere with a voltage that is 9.35 volt. Okay, so that's your Q point. Having your Q point there, we can now go and find out the GM.
My board suddenly cannot work.
So the GM
the chip suddenly cannot work.
is equal to
Yeah, I put inside the computer.
square root of
Search. Nothing. I do nothing. I just plug in the power source.
2i8, which is root of 2 times 186 micro times K, which is 200 micro. Okay, and that works out to be 273 microsiemens. Okay, R naught is infinity because lambda is 0. Okay, and therefore R naught is infinity. And therefore we can now draw the equivalent, AC equivalent, alright,
project.
by shorting the capacitor. We end up with this equivalent circuit, Ri. Now going into the source, you have a resistor Rs, okay, going into a current source from your drain, RD, and your RL. Okay, and this current source is GM VGS. Okay, right across this, you have a resistor R0, which in this case is infinite. Okay, and this current here is the current ID, and this current here, if we want to find out, this would be your R in prime, and this here will be your R in. Okay, so here we have to go and find out what is R in prime. So R in prime is if you put in a fictitious voltage between this node and ground, okay, of Vx, we'll find that the voltage between this and ground, which happens to be the gate, so this is VSG, so you end up with VSG divided by the current that is going in, alright, which is IS, the source current. So this is VGS, and the current that is going in here happens to be the current that is GM-VGS. Okay, and therefore this is 1 over GM. So when you look into the source, you will get the output impedance, which is 1 over GM. Okay, and if you work this out, this is 1 over 273 micro. That works out to be 366 K. Okay, to find out R in, so R in is RS in parallel with R in prime. And this gives you a value that is 68K in parallel with 3.66K, and that works out to be 3.47K. Now, if you want to find out the terminal voltage gain, that means the gain from the source to the drain, okay, the terminal source to the terminal drain, or in this case the output is at the drain, so is the voltage at the drain over the input, which is at the source, right? Then this is equal to the current that is flowing GM-VGS, okay, that is flowing out from your resistor, flowing out from this, okay. As it flow out, you're causing the voltage at the ground to be more positive than that at the drain, so there's a minus, okay. So the voltage at the drain is more negative than that at the ground. Huh? So you divide that with the voltage that is at the source. Okay? But the voltage at the source is more negative than the voltage at the gate. And therefore this becomes cancel, you end up with GM RD in parallel RL. Okay? And if you work this out, it is equal to 273 micro times the resistor 35.4 K
Cái tin là good. Two bucks each other.
in parallel with RL, which is 100K? No, 200K. Okay? Sorry, this is already combined. Alright, RL and RD combined. So therefore, you will end up with 9.66. A gain of 9.66 terminal voltage gain. So to find out the overall gain, okay, to find out the overall gain, you have a input potential divider. Alright. So this is VI. Okay, you want to find out the voltage from VI to VS, you potentially divide, and therefore is R in over Ri plus R in multiplied by the terminal voltage gain. Okay, and R in, okay, is 3.47 K over Ri, which is 250 plus 3.47 K multiplied by 9.66. Okay, that works out to be 8.98. Okay, so the overall gain is slightly lower than the terminal voltage gain. Okay. Okay. Then we want to find out the current gain. So the current gain is equal to the voltage at the output divided by RL. That gives you your output current. Okay. Over the input voltage divided by R in plus Ri. So this gives you VI naught over II, okay, which is your current gain. Okay, and if you break this down, you have V naught over VI, okay, multiplied by Ri plus R in over RL. Okay, so this is your AB multiplied by your input resistance, which is 250 plus your Ri, which is R in, which is 3.47 K, divided by your RL, which is 200 K. Okay, and that works out, since this here is already found to be 898, then this gives you a value that is 0.167. Okay, so your current gain is that amount. Okay, then we are asked to find the output impedance. To find out the output impedance, you kill the input source, so you end up with Ri in parallel with Rin, okay, or in parallel with Rs, and then it goes into your current source, and then it goes into your Rd, and instead of connecting to RL, you take a look at this. This is your RL. Okay. So this here is your GM VGS. Okay. And if there is this resistor R0, if there is, then R out is going to be very, very high. Okay? So, take for a moment, we look into this. We call it R out prime. Okay? Let's call it R out prime. So if we look at this as R out prime, I can redraw this, and it becomes a current source, okay, with a resistor R0 going into Rs in parallel with Ri, and I apply a fictitious voltage source Vx, and I measure this current Ix. Okay. For the convenience of breaking it down, and I can say that this is your gate, and then it goes to ground. Okay. And this current here is GM VGS. Okay, so what would happen? I can say that Ix, okay, we call this Vs, okay, Ix is equal to this current source GM VGS, okay, plus Vx minus Vs divided by R0. So these two current add up equal to Ix. And I can also say that Vs is equal to the same current Ix, okay, that is across these two resistors. Okay, and therefore I can write this equation as Gm. Now since Vg is ground, okay, I can now say it is just Vs with a minus, because VGS is Vg minus Vs, okay, plus Vx over R0 minus, instead of Vs, I can now put Ix, Ri in parallel Rs, okay, and I have an equation, here also I have to put Ix, so this becomes Ix, okay, I bring all the Ix term, this here is Ix, Ri in parallel Rs, okay, I bring all the Ix term, I will have 1 minus plus, Gm Ri in parallel Rs, okay, bring this term over, also plus Ri in parallel Rs, okay, is equal to Vx R0. And therefore we can write Vx over Ix is equal to R naught into, or rather R naught into, no need, R naught plus GM R naught multiplied by Ri in parallel Rs plus R naught plus Rs, Ri, Rs.
Sao? Vì chạy
Okay. So this, if you look at this equation, this value is very large because it has R naught, okay, plus the multiplication of R naught with this resistor times another term which is GM R naught times this term as well. So this thing here is huge, okay, it is very large, okay, and if you now parallel this R out prime, okay, and RD right now is a value that is 43K, right? You find that this is roughly equal to 43K, which is your RD. Okay? And therefore your R out is basically just the resistor RD. Okay?
When people start doing Viva, you see more because assignment.
Far worse happens that R out is infinity. Then nothing to say. Okay? And then we look at the last part for this question. What is the maximum input for the amplifier that satisfies the small signal limit? And therefore here again we say that your small VGS must be smaller or equal to 0.2 into capital VGS minus VT P, in this case VSG, okay, and that works out to be equal to VGS happens to be VI potentially divided across these two components, okay, and therefore we can substitute in that VI multiplied by 3.47K over 250 plus 3.47K, okay, must be smaller than 0.2 into 2.363 minus 1, okay, and therefore this implies that VI has to be smaller than 0.292 volt. Okay, so that means to say the input voltage must be smaller than 2.92 volt or 292 millivolt, so that the output will not be distorted. Okay. Okay, we will leave question 3 and the next tutorial to the next tutorial.